This is the video on Module 2 of the Innomat Learning and Training Package, created for the Raw Materials Academy of the European Institute of Innovation and Technology. This video shows how to deal with critical raw materials and other scarce metals with a supply chain risk in life cycle assessment. This in relationship to a business perspective. An example of a well-known material that is scarce and critical is cobalt. It is indispensable in modern batteries for cars, but at the same time it's rather scarce. During 2017, the price suddenly peaked with a factor 2.5, because traders expected that the demand would soon exceed the supply. In such situations, financial speculation becomes apparent, with heavy consequences for businesses that need the material for production. The price peak collapsed after that, since in 2019 the price was back to normal. But in the meantime, many businesses were severely hit. Since half of the mining of cobalt is in the Democratic Republic of Congo, under deploring social circumstances and political unrest, the quest for replacing cobalt in batteries intensified. Conclusion is that these peaks appear to be temporary, but may hit your business. The EU has defined critical raw materials on the basis of the chance of disruptions in the supply chain, combined with the economic impact for the EU member states. Materials are called critical when the risk as well as the impact are above a certain threshold, as is shown in the figure. There is no standard or norm to calculate criticality. There are three important systems, one in the European Union, one in Great Britain, and one in the United States of America. They're all different, but they all claim that they are the truth. The reality is that criticality is hard to calculate. The calculation system for the EU is depicted in the next sheet. To understand the calculation of criticality, we must understand the root cause of supply chain risks. There are many root causes. The so-called country concentration of mines in relation with country political stability. The issue is that when there are many countries that produce a material, the risk of political unrest affects only a small portion of the global supply, in contrast to the situation where only one or two countries dominate production. The development time of mothballed mines, in combination with the fact that a metal is a companion metal, which means that a metal is a byproduct of another metal. The issue is that it is easier for certain metals to ramp up production than for others. Third, depletion time of stocks and company concentration. This issue is related to company strategies in the mining industry. And fourth, the sudden demand growth by new technologies, which is the root cause of many financial speculations in the market of resources. And last, recyclability and substitutability, which are obviously two technical measures to mitigate the scarcity problem. The EU has developed a formula for criticality that is based on 4 of these root causes. Together with the formula for economic importance, and together with 2 thresholds, it is decided whether a material must be considered as critical or not. But don't forget that some other technical issues are not incorporated in the calculations, such as issues with regard to mining, power of mining companies, and last but not least, product innovations that influence the demand side. The accuracy of prediction of scarcity in the supply chain is therefore rather low. The formulas for critical raw materials, or CRM, cannot be used in LCA since it's non-linear, it contains thresholds, and it contains subjective value choices that are not evidence-based. So the question is what to do in LCA. The basic idea on the resource depletion score in classical LCA is simple. The materials in our Earth crust are limited, so there comes an end to its availability. This depends on the so-called yearly deaccumulation rate, which is the rate at which we are mining these materials. The calculation is characterized as follows. It is long-term, which means 100 to 1,000 years, It's not related to shortages in the current supply chains, short-term, 10 to 30 years. It's based on the so-called fixed stock paradigm. The underlying assumption is that we know the availability of materials, which comprises already produced materials, economically recoverable materials, potential recoverable materials, however at a high price, likely to be discovered through future exploration, and not recoverable. The question arises then what we take as total availability in our formula. Is it the known resource base, or the extractable global resource, or the total of resources? And is it really fixed, or is it evolving over time? The calculation of depletion is rather problematic, which means highly inaccurate, since the amount of a metal in the Earth's crust is not known within a factor of 1,000. The mineable fraction is not known, maybe some new discoveries, some new technologies, and the deaccumulation rate is not known. How high are future rates of recycling? What are the future possibilities of substitution by other materials? Nevertheless, the most widely applied LCA indicator for materials depletion is the so-called abiotic depletion potential, or ADP. It is proportional to the global consumption of a metal in kilograms per year divided by the extractable global resource in kilograms squared. So the ADP is a long-term indicator for depletion with the following characteristics. The ADP is proportional to the inverse of the estimated material depletion time multiplied by the estimated EGR. Estimations of the EGR are rather inaccurate, and this high uncertainty is squared in the formula. Calculations of the University of Utrecht show that less than 50% of the metals may deplete within 1,000 years. Since the calculation results of the ADP are rather unsatisfactory, new approaches on material scarcity in LCA have been proposed. Recently, for material scarcity in the EcoCost 2017 system. This approach is based on price volatility in the recent past as an indicator for supply risks. The basic assumption is that a certain material has a certain supply chain with its own characteristics. As long as the supply chain system does not change drastically, the supply characteristics stay the same. So the volatility of prices stays the same. So it's likely that the statistical characteristics of the past are expected quite equal to the statistical characteristics of the near future. The picture shows the cause-effect pathway for the socio-economic area of protection as defined for critical raw materials by the European Union. It starts either with a sudden technical breakthrough or with a geopolitical event, like protectionism or social unrest. This results in a supply chain disruption. Because of limited stocks in the logistics chain, this will lead to shortages of the material. In the free market economy, that will result in higher prices, rising very rapidly since all market players try to buy the material stocks that are available. Companies which need the material will see the risks of deteriorating profit margins because they cannot quickly increase the sales prices without losing market share. The weakest companies can go bankrupt, resulting in unemployment. That means that this phenomenon results in the threat of a financial depression to our society. This picture shows a typical price fluctuation over time. The price of a material is relatively stable, but it has a sudden price peak because of the characteristics of the supply chain that results in sudden scarcity. It's impossible to predict when such a price peak will happen in the future, but that it's likely to happen in a certain time span is for sure. But from statistical analysis of price fluctuations of the past, it's possible to predict the height of a sudden price peak in the future that is expected over the next 20 years. In statistics, that is called the value at risk, in short, VAR. This VAR is called eco-costs of material scarcity. It is the business risk of suddenly being confronted with the price peak of the material. From a business point of view, the price-peak ratio, which is the eco-cost of material scarcity divided by the average price, is the relevant parameter for your business risk. It may happen next year, over 10 years or over 20 years, but it's likely that such an event will take place. Here you see an example of tantalum, which is a critical material, and aluminium, which is not. You see that tantalum has now and then high price peaks, whereas aluminium has hardly relevant price peaks. These graphs have been determined for 42 metals plus 12 for the rare earth elements, available at the Eco-Cost Value website. From a business perspective, the average price-to-peak ratio is the determining factor, since it shows directly how your profit could be affected. Your business risk with aluminium is a factor 10 lower than with tantalum. The eco-cost of material scarcity is important for business and society. The eco-cost of material scarcity is directly related to the financial business risk, and these eco-costs multiplied by their import volume describe the socio-economic risk at country level as well. Innovative companies already anticipate on the issue. Examples of reduction of critical raw materials are given below. The neodymium-based magnets can be replaced by another type of magnet based on iron, recently developed, and even with a better performance. In the table you see a drastic reduction of eco-cost from 70.23 euros to 1.42 euros per kilogram. Drastic reduction of cobalt in lithium-ion batteries by a factor 10 from laptops to Teslas. The fifth assignment of this course will be to check the resource scarcity scores in eco-costs, recipe, and the EF, CML, for cobalt and nickel. Which of these scores are aligned with the trend to minimize cobalt in car batteries, and which are not aligned? I wish you a very fine learning experience with this fifth assignment. This is the end of Module 2 on critical raw materials. For additional information, you may read the paper of Voigtlander et al. On this topic in Sustainability 2019.